Everybody ready for the test on Friday? Yeah, let's get her done, right? Okay. We're going to talk a little bit more about chapter 16. Does anybody have questions before we get started? Anyone? Yes?
Did you write the test yet?
Did I write the test yet? No. I had a thing to go to last night. Yeah. I know, it's bad. I'm going to write it today, I swear. Okay, any other questions? Yes? Say that a little louder. Oh, I don't say that. I only told you one that for sure, right? There'll be more than one. So what I did tell you about mechanisms is hydration of an alkyne guaranteed, mechanism from chapter 15 guaranteed, and there's, I'm sure, going to be another mechanism. And that's good news for you because you guys usually do really well on mechanisms and don't do as well on synthesis and predicting products. So if the more mechanisms, the less synthesis and predicting products. There's going to be a lot of synthesis and predicting products too, though. Okay? Question? Say that a little louder. For the hydration of an alkyne?
Do we have to draw in the equilibrium arrows from the
No, you don't. Yeah. All right, more questions? Now's your chance. By the way, let me just say it right now. When we do a dissolving metal reduction, we take a chunk of sodium and we put it into liquid ammonia, right? Don't write NaNH3. It is not one compound. It is sodium in liquid ammonia. So if you have them written right next to each other, either leave a space or put a comma. It's not NaNH3 as one compound, okay? That's a little heads up on that. All right, let's talk about chapter 16. Anybody want me to open up Sapling chapter 16 over the weekend, or are you going to be taking a little break? I think that's a no. All right. Okay, so last time, here's what we know going into this chapter. We know that conjugated dienes are more stable than dienes that are not conjugated. And so, but how much stable? How much more stable? So we do this little experiment. We hydrogenate this. We measure the heat given off in the reaction. And since they're both going to the same compound, we can estimate, or we can calculate the stability because this one releases only 54. This releases 61. They're both going to the same thing, so that means that this has to be lower in energy to start with. And we could do a bunch of reactions like that to see that when they're conjugated, it's definitely going to be more stable than when they're not conjugated. We also want to talk about conformations of conjugated dienes. There are 3 possible stereoisomers for a conjugated diene. These are different. Okay, so what we got to keep in mind is that alkenes don't rotate. Single bonds can rotate, but not double bonds. So these 3 compounds are actually stereoisomers of each other. If you look here, this double bond is trans. Okay, and some people have trouble seeing that. That's because this group and that group are opposite each other. If you're having trouble seeing that, what helps is drawing in the hydrogens. And you can see that those hydrogens are on opposite sides of that alkene, so that's a trans alkene. And likewise, this one right here is a trans. And again, I realize a lot of people have trouble seeing that, and so it's helpful to draw the hydrogens in. And you can see that here's our alkene. This hydrogen's on the top, this one's on the bottom, so they're on opposite sides, so it's trans. So those are both trans. And then for this one here, this is a cis-cis. So here's our cis here. Again, if you have trouble seeing that, draw in the hydrogens, and you can see that the hydrogens are on the same side on this alkene. And then we can draw the hydrogens in on this side here. And so this is cis-cis. And then we have another stereoisomer where one is cis and one is trans. So this one here is cis, and this one here is trans. You can't convert from the trans-trans to the cis-cis to the cis-trans without rotating double bonds, alkenes. So these are separate stereoisomers with different physical properties. They're different compounds. There's also two possible conformations that result from free rotation about the carbon-carbon single bond. Okay, so these are stereoisomers, but there's also conformations that we have a name for. There's two conformations. One is S-trans. Double bonds are both trans about the single bond, and there's S-cis, where the double bonds are cis about the single bond. And this has to do with rotation of the center bond here. So this one right here, when we rotate that bond. And so that's on the next page. So of course that is a sigma bond. That bond in between the two pi bonds is, you can rotate that. All right, so for S-cis, this one here is S-cis. It's a little strange to look at. This is our single bond. And can you see that? And let's draw in the hydrogens here. So this is, we're not talking about the double bonds here, we're talking about the single bond, and that's why we put the S in front. Can you see that in that bond that's in between the two dienes, that the two hydrogens are on the same side? So that means that the two alkenes here are also on the same side of this bond here. So this is S-cis. So this is the orientation of the two conjugated double bonds here. And they are on the same side here, so that's S-cis. And then if they're on the end, and they can also, so this can also rotate though. To S-trans. This is what the S-trans would look like. And let's see how the heck we did that and what we're talking about here. So let's orient ourselves. This is the bond that's in between the two alkenes. Here's the bond that's in between the two alkenes. Okay, so we can't change this here. We can't change the fact that this is trans and this one's trans. So there's still trans in the product, except we just rotated it, so we're looking at the orientation here of the two alkenes about that center sigma bond. And can you see that when cis is rotated, that this hydrogen is up and this hydrogen's down? So these two double bonds are actually trans to each other. Can you kind of see that if you change your perspective a little bit? So this would be S-trans. So very strange, but it's a terminology that we're going to use here. So this is S-trans. And definitely S-trans is almost all the time, not all the time, but almost all the time more favored. So these are going back and forth. This double bond and this single bond in the middle is rotating really fast. There's two orientations. But if you look here, we have a little bit of steric hindrance with these two hydrogens here in the S-cis conformation. So there's a steric hindrance here. Steric hindrance. So the S-trans is more stable. More stable conformation. And it turns out that the barrier to rotation here is 4.9 kcal per mole. Is 4.9 kcal per mole. At room temperature, how much energy do we have for kinetic energy for rotation? Do you remember that from 51A? 20 kcal per mole at room temperature is what we have available. At room temperature, we have 20 kcals per mole available for this rotation. So it means that we have more than enough energy for that rotation. So 20 kcals per mole available. So therefore, there is free rotation. Rotation at room temperature. All right, the second example here, can you see that there's more of a problem with steric hindrance? This is the S-cis conformation. And these two methyls are actually, that's a worse steric hindrance. So we're going to have even a longer arrow and even shorter arrow the other direction, if I can, there, because it's less favored, and so the S-trans is more favored. And let's double check that we haven't made a mistake. So let's identify here, this is our S-trans. Is definitely favored. And let's make sure that we've done this right. So let's go ahead and zero in on what we're talking about right here. That bond right there. And very helpful to put the hydrogens in. If you look at the orientation of the two alkenes, they're on opposite sides of that single bond that's in the middle. If you look over here on this side, they are on the same side. If you look at what we can't rotate, let's use a different color for that. The orientation of this bond and this bond here, that's cis, right? Not S-cis, that's cis. We're actually talking about the alkene. This is cis. And likewise, right here, that's cis. So we don't want to change that. The only thing we can change is that center bond, and this is cis. And what you want to be able to do for the final, not for midterm 2, is be able to rotate those without making a mistake, without changing things that you're not allowed to change, which is whether you have cis or trans. You can change S-cis to S-trans, but you can't change cis to trans. Most conjugated dienes prefer the S-trans conformation. So most of the time, we're going to see the S-trans as the more stable conformation. There are some exceptions here. This one here, not obvious, but we actually have a short arrow to the right and a long arrow to the left. And if we draw out and draw in all the hydrogens and the methyls, this would be the S-trans. And it turns out that there's steric hindrance with these guys, these two, the methyl and the hydrogen. It doesn't look like they're super close together, but if we drew out these hydrogens, let's draw that out so you can see what I'm talking about. That methyl and that hydrogen are getting a little bit too close together, right here. Okay, so there's steric hindrance, more steric hindrance in the S-trans. So in this particular case, the S-cis is favored. And that's because of the bad steric interaction. In the S-trans conformation. Oh boy. In the S-trans conformation. And I would agree that it's difficult to see why these two methyls are not in a bad steric interaction, but this is actually worse. Yes?
What's the variance rotation for the S?
Don't have that number off the top of my head. I should look that up and include that next time. Yeah. So maybe make a model, and if you want, well, I have lots of models in my office. You can make a model and maybe be able to see this a little better, but that this is better than this, okay? Seems like that might be worse, but this is actually worse. And then, of course, this one here, can this bond between the two double bonds, can that rotate? It can't when it's in a ring. So this is fixed in an S-cis conformation. All right, so that's just a little terminology, cis, trans, S-cis, S-trans, what's the difference? And we're going to need to be able to do this when we talk about the Diels-Alder reaction, which is coming up a little bit later today. But first I want to talk about a familiar reaction to you, and that is electrophilic addition. Okay, so this part of this chapter should be really easy if you know chapter 10. If you don't know chapter 10, likely you'll know it before Friday, since that's on the test. Which one of those alkenes is the most reactive in this first example here? Left or right? The one on the right, if we protonate the one on the right, we form a tertiary carbocation. If we protonate the one on the left, the best we can do is a secondary. So we're going to protonate the one on the right, definitely. And so that one is more reactive. Because it forms the most stable carbocation. So pretty straightforward question. We can easily write the answer there. Let's just go through the mechanism here, just as a little recap. So we're going to form the tertiary carbocation, and then chloride comes in and attacks. So it requires a little bit of thinking about what's going to be the most reactive. That's going to come in and attack. And so the product is this one here with the chlorine on the right-hand side. Don't need to show stereochemistry here because this carbon at the end is achiral. There's no stereocenters here. All right, so that would be our product with one equivalent of HCl. If we have two equivalents of HCl, we're gonna protonate both sides. Yes. Question? Did I hear a question, or was that a bless you? Bless you. Sounds a little bit the same from here. Okay, so that means we're going to protonate both sides. I won't go through that mechanism, but this is what it would look like. So excess or two equivalents. I could write either. It's going to do it on both sides. So that's when we have isolated dienes. A little bit different story when we have conjugated dienes. So really, this is the last time in this chapter that we talk about isolated dienes. The rest of the chapter, we're going to talk about conjugated dienes. All right, so let's see what happens when we do the same thing with a conjugated diene. All right. symmetrical dyene here, so it doesn't matter which side we protonate. If it wasn't symmetrical, we would protonate the side that would give the most stable carbocation. We'll see one of those coming up. I should do this down here. Let's kind of move, let's just move this down here. So pretend that I actually redrew that and moved it down here. Or maybe I'll just erase it and do it the right way. Come on. You can leave it there. You don't have to erase your pen. All right, so I'm just going to do the same thing. HCl. Let's go this way. Let's not go that way. Oh my gosh. We'll go and erase that in a second. Okay, so what do we have here? We're going to have the proton go on the end. So that's right here. There's also 2 other protons here. So it will look like that, right? But that's an allylic carbocation, and whenever we have allylic anything, that includes radicals, that includes carbanions, that includes carbocations, we want to draw both resonance structures, because that's resonance stabilized. So we're going to draw the resonance structure for that. So then this is going to go here. And I am deliberately putting hydrogens on the end here, because the most common mistake I see students do is to lose that last carbon there. So I'm going to be deliberately trying to draw hydrogens on the ends of these. And I encourage you to do the same thing on a test. Now, definitely the secondary carbocation is more stable than the primary carbocation, but they're both allylic carbocations, so they're both stable enough to form. And so, and then the second step, and I'll change colors here so we don't get confused with the arrow pushing. I'm going to have chloride ion come in. It can attack this carbocation, or I can have chloride ion come in and attack this carbocation. So let's draw the product here. Chloride goes here. And we also get one where the chloride goes on the end. And I'm taking all the time, extra time to draw those 2 hydrogens in, because the most common mistake is for students to lose that carbon that I just drew the 2 hydrogens on, okay? So let's look at what just happened here. We have, what did we add? We added this and this. And here we added, there's the same hydrogen and the chloride's there. We have a different name for each of those. This is the 1,2 product. And this one here is the 1,4 product. So the 1,2 product, the hydrogen that you just added on and the chlorine are on adjacent carbons. Doesn't matter if they're in the middle of the molecule or at the end, it's 1,2. Here, 1, 2, 3, 4, if you count carbons, the hydrogen is on carbon number 1, and then the chlorine is on carbon number 4. So this is the 1,4 product, and this is the 1,2 product. And we will get both of those forming. And that's all because the allyl cation is stabilized by resonance. Questions so far? Anybody? Yes? If we were going to talk about stereochemistry, yes, you will form enantiomers because you have a planar carbocation and you could get attack of the chloride on either side. Okay, right now we're not going to worry. Right now we're not focusing on stereochemistry. If the conjugated diene is not symmetrical, the major products of the reaction result from addition to the most reactive double bond, the one that forms the most stable carbocation. So don't forget about that. Don't forget about that on the final, and don't forget about that when you do chapter 16 sapling. Because there's 4 possible products and you only get 2 of them if you're not worrying about stereochemistry. So which double bond is the most reactive, the one on the left or the one on the right? Left will make a tertiary allylic. If we do the one on the right, it will make a secondary allylic. Tertiary allylic is more stable. So this one here is the most reactive. All right, so let's add HCl to the most reactive. Arrow comes from the pi bond. We grab the hydrogen. We break the hydrogen-chlorine bond. So that gives us a tertiary carbocation. But whenever we make an allylic anything, we want to draw resonance structures. So this is an allylic carbocation. So let's draw the resonance structures. I'm not going to do the arrows for it because I don't want you to get confused with the chloride ion attacking arrows. So this will be CH3 here. The double bond moves over 1 to the left. And then we have CH, and then we have CH2 plus on the end here. So those are the 2 resonance structures for that allylic carbocation. And then the chloride ion can come in and attack on either side. Some of the time it will attack on the left-hand side, and some of the time it'll attack over here on the carbon that's on the right-hand side. And if it attacks on the left-hand side, you get product number 1. If it attacks on the right-hand side, you get product number 2. You do not get any products from protonation on the carbon on the right. So if you were to protonate this one first, you get 2 different products, and you don't get those. Let me draw those 2 products for you. So when you run across this problem in sapling, you'll see, oh, I'm protonating the wrong one. Not. These would be the other 2 products you would get if you protonated on the other side, and you don't. And again, we're not even considering stereochemistry here. That increases the number of things that you can get. Okay, so you don't get those. Big X through that. Okay? And so these would be from addition to the other double bond first. And you don't get those, so you certainly do not want to include those on your exam. So what's the one we get the major of? Do we get the 1,2 as the major? Do we get the 1,4 as the major? And really, it depends on the conditions of the reaction. So that leads us right into kinetic versus thermodynamic products. And this tends to be a question that people talk about that's on the DAT and the MCAT. Of course, nobody knows the new MCAT very well, the wild, wild world of the new MCAT, but kinetic versus thermodynamic products is something that I've seen on MCATs before and DAT before. All right, so I want to talk a little bit about that. When a reaction produces more than one product, the product that's formed more rapidly is the kinetic product. Does that make sense? That seems logical. Fast is kinetic. You think of fast speed. That's the kinetic product. And the product that's the most stable is the thermodynamic product. Okay, so that's something we want to keep in mind here. Product that forms faster is kinetic. The product that predominates at the equilibrium is called the thermodynamic, and it's always going to be the most stable product. All right, so for many organic reactions, the most stable product is the one that's formed more rapidly. That is, the kinetic and thermodynamic products are the same. For electrophilic addition of HX to a conjugated diene, however, the most stable product is formed more slowly. That is, the kinetic and the thermodynamic product are different. All right, so, I've seen one example where that's not the case, but we'll just stick with this for now. All right, so it turns out if you add HBr to this conjugated diene, and again, it's not symmetrical. I mean, it is symmetrical, so it doesn't really matter what we do. But if you do it at minus 80 degrees centigrade, you get 1,2 and 1,4 addition, but you get 80% 1,2, and you get 20% of the 1,4 addition product. And it turns out that the 1,2 is the kinetic. This is the kinetic product. Which means it's formed more rapidly. And if you are at very low temperature, which minus 80 degrees centigrade is very low, the kinetic product is going to predominate. Over here we have the thermodynamic product. Which means it's more stable. Why is that more stable? Why is the 1,4 product more stable? How many R groups are bonded to that alkene? 2, and in the kinetic product there's only 1, so it's a more stable alkene. So more stable because it's a more substituted double bond. All right, so let's look at the effects of temperature. What happens if we run that reaction at 40 degrees, or we can actually run the reaction at minus 80 and now allow it to warm up to 40. Doesn't matter how we do it. We can do it both ways. And it turns out that when you allow that reaction to warm up, or you run the reaction at 40 degrees, you get 15% of the kinetic product and only 85% of the 85% of the 1,4. So the most stable product now predominates. So why does the product distribution change? In order to answer that question, we need to look at the energy diagram. So let's look at the energy diagram and see if we can figure out what's going on here. The first step is the same for both of these reactions. If the kinetic product, so the first step is going to be the same for both. If we look at the second step, the kinetic product is the one that has the lowest energy transition state, right? So this is the 1,2 is the kinetic product here. And at low temperature, the molecules have less energy, right? They have less energy at lower temperature. And so they're going to take the lowest energy pathway here. And so that's why that's going to be the major. Most of them are going to take the lowest energy pathway, right here, which gives the 1,2 product. When you have the reaction at a higher temperature, then the molecules are more energetic, and so more of them have enough energy to overcome this higher energy barrier, which actually leads to the more stable product. All right, so this is the transition state for the 1,4 product. And the lower energy transition state is for the 1,2 product. So this is the transition state for the 1,2 product. All right, now if we run this reaction at 40, we get our major product is going to be the most stable. It's going to be this one. If we run it at -80 and then allow it to warm up to 40, we still get this one as the major product. So that means the reaction's reversible, right? If we start off with 80% kinetic and we warm it up to 40 and then we get 85%, that means it's a reversible reaction. All right, so let's look at what happens. So we're at low temperature. Most of the molecules undergo this lower energy pathway. In order to do the reverse reaction, and that's a reversible reaction, we got to go back to this intermediate. Okay, so that means that to go reverse reaction, we have to come up with this much energy to go back that other direction. And at low temperature, the molecules don't necessarily going to have very much energy to do that. If we're at a higher temperature, we're going to have both kinetic and thermodynamic. But can you see that once we form this thermodynamic product, we're much less likely to go back again, right? Why would that be? Much higher energy of activation. So what we end up getting is as soon as we form the thermodynamic product, it doesn't go back again because it's too high energy for it to go back. It stays there. So we call this a thermodynamic well. It's like the product has fallen into the well and it's too deep to ever go back again. So even if we so most of the time we're going to form the kinetic product faster because it's a lower energy pathway even at 40. But once we form the thermodynamic, it's not going to go back again. So eventually we're going to get a thermodynamic mixture where most of it is going to be this 1,4 product. So let's look at the bullet points underneath this and go through that. At -80, there's not enough energy for the reverse reaction to occur. Okay, so that's, even though this is available, it's still at a high energy of activation for molecules to come up with at -80 to go up that energy hill barrier. At 40 degrees, there's enough energy for the reverse reaction to take place. The products can revert back to the common intermediate. The products can now interconvert to form a thermodynamic mixture. And as we said, once you form this product, it tends to stay. Thermodynamic product reverses less readily because it has a larger energy barrier than the kinetic. So that's what we're talking about right here. Because this energy barrier is too high. Let me do that in a different color. Huge energy barrier. This would be EA for reverse reaction for the thermodynamic product. And it's just too high. It's not going to go the reverse reaction. So there's some terminology used. That's when a reaction is irreversible under the conditions of the reaction. It's said to be under kinetic control, and the relative amounts of the products will depend on the rates at which they are formed. So at -80, we say that we are under kinetic control. Molecules are not energetic enough to do the reverse reaction. But at 40 degrees centigrade, on the other hand, we are under thermodynamic control. And when we are under thermodynamic control, we always have reversible reactions, and we're going to always end up with the more stable product predominating. Okay, so the question is, we said the 1,2 product is kinetic. Why is that actually formed more rapidly? Let's look at the mechanism really quickly and see if we can figure this out. So we have HBr here. All right. Immediately after we have that step, do you see how the bromide ion is right there? It's very close to that. It's right where that carbocation is formed. It's much easier for this bromide ion to come in and attack that carbocation because it's in closest proximity to that carbocation. To form the 1,4 product, this double bond moves over. We have the carbocation at the end, and the bromide has to migrate over there to attack. And it has to migrate over. It's got to be in the right orientation and all that kind of stuff. So this forms more rapidly because of we call it the proximity effect. They're so close to each other, that reaction is going to be faster than the bromide ion having to migrate. So the bromide ion is close by. So we call that a proximity effect. And when you're at low temperature, the molecules are not moving very quickly. They're not very energetic. For that bromide ion to go over there and move over to the other side is going to require a lot of energy. It's not going to happen as quickly as it is if it's just right there. So therefore, it attacks faster in this position. All right, questions? Anybody? So it looks like we have HBr addition to dienes, we have HBr addition to isolated dienes, and we have HBr addition to conjugated dienes. So that's 2 reactions so far in chapter 16, right? There's only one more reaction we have to talk about in chapter 16, and that's the Diels-Alder. We're going to spend the rest of this chapter talking about Diels-Alder. So Diels-Alder, a very famous reaction. This is what it looks like. Alkenes and alkynes add to conjugated dienes to form 6-membered rings. It's a beautiful way to make 6-membered ring, 6-membered cyclohexene rings or cyclohexadiene rings. Okay, so this is what it looks like. I like to put a dotted line between the 2 ends of the pi system. We're going to be moving electrons around in a circle. It doesn't matter whether we go clockwise or counterclockwise. We're going to be moving electrons around in a circle. And so all you want to do is you want to start from one of the double bonds. I'm going to go counterclockwise here, but you can also go clockwise. So if you look at what we're doing, we're getting rid of this pi bond here, and we're going to get a double bond right here. We're getting rid of the double bond here and using that to make a new bond between the 2 ends here. This double bond here from this alkene is going to move over here to make a new bond here, and that's how we're making that 6-membered ring. So this is what it would look like. Whoops, I drew that wrong. Put the double bond on the wrong side. Don't want to do that. Double bond's right here, huh? Yes? Follow the arrows, the double bond's right there. If we have an alkyne, same idea. I'm going to have dotted lines connecting the 2 ends. We're going to move electrons around in a circle. This time I did counterclockwise here. I'm going to go clockwise. Does not matter the direction. And it turns out that all of these bonds are being made and broken simultaneously. This is a concerted reaction. So we get a double bond here. We've broken one of the pi bonds in the alkyne, but not the other two, so we have a double bond on the other side. So the alkene or the alkyne is called a dienophile, a lover of dienes. So romantic, right? This is a dienophile. It loves dienes. And the alkyne is also a dienophile. It loves conjugated dienes, okay? And then this is the diene, of course. So there's the diene and there's a dienophile. The reaction is a 4+2 cycle addition because the ring is formed by the interaction of 4 pi electrons on the diene with 2 pi electrons on the alkene or the alkyne. So there's 2 electrons for each of these pi bonds. So this is 4 pi electrons. So let's label that. This is 4 pi electrons. And this is 2 pi electrons. This is 4 pi electrons. The triple bond has actually 4 pi electrons, but we're only reacting 2 of them. So we would also call this a 2 pi electrons. The other 2 electrons in the other pi bond are not reacting. So this is a 4+2 cycloaddition. It's only one of a type. There's a broad category of cycloadditions. This is one example, and we're going to be focusing just on this one example. All right, let me give you some examples, some more examples here. Let's draw the products here. So super simple mechanism. I'm going to go counterclockwise here. 6-membered ring. So mechanistically, very simple, but we have a lot of issues that we have to deal with in this reaction, stereochemistry, regiochemistry, which makes it more complicated. All right, so that's what that looks like. I'm not attempting to draw any stereochemistry at this point here because we're going to talk about that coming up. And then we have this one here. This is more complicated to draw, so I'm going to show you 2 different ways to draw this. The first one is going to be the more complicated way to draw this. You love that, don't you? So we have a double bond here, we have a double bond here. And we have the CO2CH3 here. I knew you'd like this. Okay? So what it makes is kind of like a little house. You know, there's the roof of a house with a little peaked roof, right? It's a bridged bicyclic structure, and that's why it's hard to draw. Bridged bicyclic structure. And we call this one right here, we're at the juncture of the 2 bridge. This is a bridgehead position. And this one over on the other side is also a bridgehead position. And if you look at this, if you examine this structure, you can see that we have a 6-membered ring right here. If we count here, 1, 2, 3, 4, 5, 6. We also have a 1, 2, 3, 4, 5-membered ring here, and a 1, 2, 3, 4, 5-membered ring on that side. There's actually 3 different rings here. All right, if you don't like drawing it that way, let me give you an easier way to draw this that you'll like better. And this is going to be a bird's eye view, as if we were a little bird on top looking down from the roof. If you're coming from the top and looking down on this, then this little bridge here is sticking straight up towards you. So this would be the bird's eye view. You like that better? You got to make sure that this is obvious that we have a bend here, okay? So coming straight out at you. Another way to draw. Okay, so perfect stopping point. We will continue this on Monday. I'll see you on Friday for the midterm.